You have stuff for me. Okay. I started with a regular ordinary integral. Integral of f of x dx. Then I changed that up and I created a path integral, a line integral. The integral across some curve C of a function of two variables, and I integrated that with respect to arc length. I want to generalize this further. I want to think about a function of three variables. And then I have some surface in 3D. Just like the line integral measured the height of the fence that followed that funky path, what I'm thinking of now is trying to do like a double integral, but instead of going on a flat region in the xy plane, I go on some surface in 3D. And then I'm adding up f of x, y, and z. So I really don't know how to draw a fence under this because I don't know how to draw in 4 dimensions. But the idea is still there. The problem is the way we describe this surface S. Because I'm either going to do this integral where my surface is some function, or I'm going to do this where my surface is parametric. So now it depends on whether I'm describing my function, my surface as a function of two variables, or I'm describing it parametrically, again, as a parametric function of two variables, because that changes the way we write D capital S. Now, D capital S is what we did on Wednesday. That's our surface area differential. So, we're going to have to do both of these because it's going to depend on what our surface looks like. If I have a nice surface, an easy to deal with surface, then I can just go directly to a function. If I have some funky, twisty surface and I need it described parametrically, then I'm going to use that R version. And then it's just how we do the double integral. If S is the graph of g of xy for some particular domain full of x and y values, then the double integral on the surface gets done by replacing z with g of xy and replacing ds with the surface area version in G. And now that integral is done on the domain D. Now I can already see on your face, you're like, right. So let's do an example. and see if I can make this make sense. Let's consider a function that's fairly simple, z squared. And S is the part of the cone z equals square root of x squared plus y squared inside the cylinder x squared plus y squared equals 4. So I'm starting with 3 different equations here, and I need to figure out how they relate to get the thing I'm trying to figure out. The function I am describing, f, that's the thing that goes inside my integral. Everything else is about the surface. Let's start with the region we're going to do the integral over. I'm going to integrate over S. I need to know what S looks like. I can draw a picture. I don't have to. I think the picture will help, but it's not required. Drawing a cone. Z equals square root of x squared plus y squared. That's a cone sticking up, whose center point is at the origin. It goes up at an angle of 45 degrees. I'm a crap artist, but there we go. Here's the part in the front and in the back, to the right and to the left. But I only want part of this cone. I want the part inside the cylinder x squared plus y squared equals 4. So I cut this off. Where? Where it intersects with the, where what intersects with what? So the cylinder intersects with the cone. That's going to happen where? It's going to happen where those two things are equal. Which means, where does that occur? B squared is 4, or Z is 2, right? A height of 2, and also a circle of radius 2. So we have a circle. I've actually drawn that circle up here. Let's label it, and we'll say that this is the circle of radius 2 at a height of Z equals 2. So I can think of this like a cone-shaped coffee filter, right? A drinking cup out of one of those old-fashioned tub machines. Now, I want to know, I want to add up Z squared at every point on the surface of this cone. So I'm going to take little samples, I'm going to add them all up, and I'm going to shrink the sample, I'm going to do an integral. The integral gets done in the XY plane. Go back to the formula up here. S is the graph of some function for XY in some domain. Then this integral on S becomes this integral on D. S is in red here. What's D? I keep using this phrase that it's the part of the XY plane that the surface lives over. If I look down at this from the top, what do I see? A circle. What circle? This circle. The circle of radius 2 centered at the origin. My surface is contained inside this circle. So what am I doing when I do this integral? When I go to do the integral of f ds, the double integral over the surface of z squared d capital S now becomes an integral over the domain D of what? Z gets replaced by the surface equation. The surface equation is the cone. What's ds get replaced by? Almost. I need the surface area piece and the dA. The dA goes way here at the end. What goes in there? Okay, wait a minute. 1 plus gx squared plus gy squared. What's g? What g? G is the surface. G of xy, that's my cone. What's g with respect to x? Take a partial derivative. And gy? Same with a y on top. So up here, I'm going to get x on square root of x squared plus y squared quantity squared. Here, I'm going to get y on x squared plus y squared square root quantity squared. I really didn't leave myself enough room. I apologize. Hey, wait a minute. Let's do the algebra. What happens when I simplify here? What happens when I simplify here? Because what I get is x squared on y squared. I'm sorry, x squared on x squared plus y squared on x squared plus y squared. Add those together, you get 1. Then I have the plus 1 on the outside. Hey, dA. Please notice the absolute best part of what I've done. I've turned an integral on some weird ass surface into a regular ordinary double integral. And what is this D? What does this D represent right here? Yeah, but what is it? It's a domain. But which domain? The circle at the bottom, the circle of radius 2 centered at the origin. I'm integrating a function on a circle. What's the easiest way to do this integral? I'm going to do polar coordinates. Okay, switch to polar coordinates. What is this integral? The integrand itself, x squared plus y squared becomes, and then I have the square root of 2, dA becomes, and my bounds are, ta-da! Hey, wait a minute, that's really an r cubed, right? And square root of 2 is a constant, I can take it out front. Root 2, integral 0 to 2 pi d theta, integral 0 to 2 r cubed dr by my corollary to Fubini's theorem. It's a good thing we know how to do all these double integrals, right? Ta-da! Gesundheit. Keep your head on. It's okay. The integral of d theta is theta. The integral of r cubed is r to the 4th over 4. Plug and chug all my numbers, and I get 2 pi times root 2 times 16 over 4. That's 4. That's 8 pi square root 2. Ta-da! When we did a line integral, we figured it was the area under the curve of this function along the twisty path that was our line. When we did a double integral, we thought of it as the volume of something, right? But what I've really done is I've distorted that idea. This square root of 2 right here says you're not looking at the volume on the flat disk, you're looking at the volume on the cone. We've changed the geometry of the universe. We're not looking at a flat thing, volume under. We're looking at the cone and the volume, quote, under that. But it's weird because the cone sticks up in a way that regular volumes don't. So I have to change this. And the image is, I need to be much more under hallucinogens to actually figure out what this looks like. I don't do enough drugs for that, man. Questions? I will say this. This is easier than a line integral. Why? What was the hardest part about doing the line integrals? All the parametric crap, right? I didn't have to do anything parametrically here because it was given as a function. When I do have to do parametric behavior, I better be given the surface, because figuring out the surface, that was a pain in the ass, right? What is the equation for the parametric description of this cylinder? What is the equation for the parametric description of the sphere? Unless I'm doing things I know the parametric description of, that's going to be the hardest part. We'll do that in a minute, but we'll do it for surfaces we know. Questions? Okay. Please note that the double integral on any surface of 1 ds, that's going to be our surface area. Because then all I'll have is that square root of 1 plus gx squared plus gy squared, that's the area of G. But what if I had an actual physical object? I said a coffee filter earlier, right? But if I go down to the lab over in Boyle, they'll pick up filter paper, and filter paper has a very particular density, right? So I can pass my solution through it, pull out my precipitate, it's been a long time, weigh it, and not have to worry about the weight of the filter paper because I know how much the filter weighs. So I've teared that part out. If I have a density function, I can take our ideas of centers of mass and moments of inertia and all of that, and I can turn it into, instead of just doing the integrals on curves, I can do the integrals on a surface. If you have a bowl of a particular shape, where's its center of mass? Well, if I know how dense it is, it's thin up here and thick down here, I can do all those same double integrals we did. The formulas now just become ds instead of dA. There's an example on page 1124 where all of these formulas are. Mass uses the density equation, and the centers of mass use exactly the same idea. Multiply by x times the density, y times the density, or z times the density. I will do this very, very rarely. I'll leave that to the physics department. So what happens if I take this same problem we were just looking at and switch from a function to a parametric surface? Good luck. Well, that is really three functions of u and v. And usually I'm given some range for u and v when I describe my parametric surface, like our spiral piece of tube, right? Our helicoid, or our unit sphere, or our plane made up of two vectors, right, Mia? The one you were asking about yesterday. I can describe a surface this way. I'm going to do a very similar problem. I want to do the double integral of x squared ds over, yeah, I'm going to call it B. You know why I'm going to call it B? It's the surface of a unit ball. That's why I changed it to B. I don't care. If you want to use S for sphere, that's fine. It works the same way. I just get tired of seeing S in the bottom and S in the integral. Makes me twitchy. But that's a personal foible of mine. So, how do I do this problem? I need the equations for my sphere. And then I'm going to say this. The integral of f of x, y, z ds becomes the integral of f of r of u v. And then I need the ds part in u and v. What's the ds part in u and v? This is what we looked at on Wednesday. What goes here? And now I'm integrating over d, where d is the description for u and v, and this dA is either du dv or dv du, depending on which way is easier. Or maybe we'll switch to polar or something, depending on the way u and v are described. Oh, that plays the same role for this problem that this played for this problem. Okay. On Wednesday, we figured out the parametrization for a sphere. What are the parametric coordinates for a sphere of radius 1? I'm going to cheat. I'm going to use spherical coordinates. But the radius is 1. So I can use the spherical coordinates we already know and use regularly. And you should have written down on your formula sheet, so we already have it. So nice when I get to cheat. X is equal to R sine phi cosine theta. Y is equal to R sine phi sine theta. And Z is equal to R cosine phi. But that means I'm using theta and phi instead of u and v. The horror, the horror. It's the end of the world. I don't care. All I need to know is what is the range, because this, that's D. Theta goes from what to what? 0 to 2 pi. Phi goes from 0 to pi. Which means, as far as theta and phi are concerned, this is a box. So I can integrate d theta d phi or d phi d theta. Doesn't matter. But I need this. So R of theta phi is sine phi cosine theta. Sine phi sine theta cosine phi. I need my partial derivatives. I need R with respect to theta. I need R with respect to phi. Now, the problem is that from here on down, there's a lot of ugly, nasty trig work involved. I take the derivative with respect to theta. The derivative cosine is minus sine. I take the derivative of sine, I get cosine. There's no theta here at all, I get a 0. I now take the derivative in phi. The derivative of sine is cosine. Where sine is cosine. Derivative of cosine is minus sine. I think you need to leave about 4 inches of paper. But when I finish, it takes a lot to get there. I'm going to do that cross product. I'm then going to take the length of it. Oh my God. There's a lot of ugliness that happens here. Same time, wait a minute. That looks familiar. What's the radius of this ball? 1. What's dv for spherical coordinates? When you do a triple integral in spherical, what do you put at the end before the d rho d theta dc? Almost. I put rho squared sine theta. The rho is equal to 1 in this case. So I want to do my integral. Double integral over the ball of x squared ds becomes the double integral over my domain D of x squared length of the cross product dA. Yes, sir.
So that's not because we're doing the spherical coordinates.
I actually did all the trig work. There's my cross product. There's its length. It's not.
You know, well, it's not necessarily gonna give right, it's just
That's just what it turned out this time. Like I said, it takes a while, but the trig is in there. Hey, wait a minute. I know how to do this integral. Because we're going over this domain D right here, yes? So that means this is the integral from 0 to 2 pi of a bunch of stuff in theta, and the integral from 0 to pi of a bunch of stuff in phi. And all I have to do is separate that and do 2 trig integrals. 0 to pi of sine cubed phi d phi times the integral from 0 to 2 pi sine squared theta d theta. And I know how to do these integrals. I'm not happy because they're ugly integrals in trig, but I will learn to live with that. Ugly is in the eye of the beholder. Chapter 7, section 2, I'm doing a bunch of trig substitutions. Section 3, I'm doing a bunch of trig substitutions. No, 7 and 2. Now I got to do the double angle formula with the sine squared. I think cosine is 1 minus 2 sine, so it's going to be 1 Oh. No, I have to yell at myself. Wait, I have a problem. It's not a huge problem, it's a little problem. I'm glad I caught it now. I made a mistake right here. Where's the mistake? Sorry, what's the mistake? I'm doing the integral of x squared. X is sine phi cosine theta. Which means fortunately I haven't actually done any of the work yet, but it's cosine squared. So that gives me cosine squared 2 cosine squared minus 1. So it's 1 plus 1 plus cosine 2 theta d theta. I never remember whether it's plus or minus. And then I said, wait a minute. My notes say plus. Why am I seeing minus? Because I just didn't work out in my head because I wrote down the wrong equation. If you screw it up, you're going to screw it up everywhere. My fault. Okay, but now I can do this integral. So u equals cosine of phi, du is, where is sine is cosine, or cosine is minus sine, so I'm going to get minus cosine phi plus cosine cubed phi over 3, insert pi. And then here, I'm going to get theta plus 1/2 sine 2 theta, 0 to 2. Those are both regular ordinary U substitutions. Yay. Cosine of pi is -1. -1 cubed is also -1. Cosine of 0 is 1. Two pi minus 0. Sine of 2 pi. Oh, wait, sine of 4 pi. What's sine of 4 pi? And sine of 0. What do I get here? Oh. Except for the fact that I made a typo again. You're absolutely right. Again, the mistake is mine. The mistake is back here in my double angle formula. What should happen? There should be a 1/2 out in front there. Which makes it 4 on 3 times 1 pi. So the big idea here is that I can take an integral on any surface I want and convert the surface to a regular double integral. There is an example on our Canvas page that I stole from an old version of this textbook that uses a really complicated surface. Please notice this is the region enclosed by a cylinder x squared plus z squared equals 1, the plane y equals 0, and a slanted plane. This actually has 3 different surfaces glued together. It's got the circle over there on your left edge. It's got the lateral surface of the cylinder. And then it's got this angled ellipse on the right. So if I want to do the surface integral, I actually have to do 3 separate integrals. I have to integral on one surface, the disk on the left, then the surface of the cylinder, and then that slanted. Now notice, I'm going to do those independently. Here is the integral on the first surface. Hey, it's the integral of x, y, and everywhere on that surface, y is equal to 0. I'm integrating 0. I'm done. That's 0. But to do the second one, I have to describe a cylinder, right? Here's my parametric description of that cylinder. Cosine of theta, sine of theta. But I start when y is 0, and I end when y reaches that funky edge plane. So that's where y is equal to 2 minus x. 2 minus x. So here's r of y and theta instead of u and v. My derivatives, my cross product. Hey, look, that turns out to be equal to 1. I rigged the problem. I rigged the problem. I cheated. But then I can actually do the double integral. But that integral goes from 0 to 2 pi and then 0 to 2 minus x. That needs to be on the inside. This is a type 1 region. And that turns out to be minus 2 pi. On my third surface, I've got an angle. So when I think of this surface, that cross product should stick out from that surface somewhere, right? Well, there's the parametrization. Z equals 2 minus x, right? Sorry, y equals 2 minus x. I can think of that like it's a function. Y equals 2 minus x. So I can do g of x and z. Or I could use my parameters, x and z. And then I can do a parametric description. As you can tell, I do parametric descriptions more than I do functional descriptions. It's just the way I was taught. So here's the version for the parametric description. And here's that integral. And so when all is said and done, I just add up those 3 integrals. I posted this. This is on our Canvas page. So please take the time to look at it. But there's something even more special about this surface. This surface is closed. There's a surface with a finite bounded region inside it. This is where I need to start talking about the ideas that we mentioned yesterday about a surface having an upside and a downside, an outside and an inside, a left and a right. This surface has an orientation. I can tell you whether I'm on the outside of the surface or the inside of the surface. In my Mobius strip, I can't tell you which side I'm on because the orientation is not consistent. So I'm going to make sure that we are only dealing with surfaces that have nice orientations, as opposed to a inconsistent. As I walk around, I was pointing towards the inside, but as I walk around, all of a sudden I flip and I'm pointing towards the outside. I get back to the same spot and I'm on, quote, the wrong side. So I don't know whether I'm coming or going in this one. But if I have an oriented surface, then I could say, oh, well, the normal vector either goes up or it goes down. And I can tell you which way I want to think of the surface. The advantage is that these normal vectors can be described by the cross products we were taking. Because if I have the partial derivative with x and the partial derivative with respect to y, I take fx cross fy, I'm going up. If I take fy cross fx, I'm going down. So I can decide which one I want to use. And most of the time, I want a normal vector that points upward. An orientable surface has an orientation on it. I can tell which is the left side, which is the right side. I can tell which is the up and which is the down. The orientation is defined by a normal vector. I'm going to make my life easier, and I'm going to make this a unit normal vector. If my surface is a function, then the normal vector comes from hey, that's a familiar looking thing. This is the tangent plane idea, and that's the length from our ds, isn't it? As opposed to if S is given parametric, then the normal vector is the cross product, RU cross RV, divided by its length. On a closed surface, I want the normal vector that points out. This picture on page 1128, a positive orientation either points up or out for a surface. We're going to talk about positively oriented the same way we talked about positively oriented curves. So I'm going to talk now about positively oriented surfaces. A surface where my normal vector goes up. But I will continue this discussion on Monday. I will see you all then. Have a wonderful rest of your day.